All right. Hello, everyone. So today is lecture number 9 and of our course on quantum computing. And let's recap of what we've done last time. Okay, so last week, or well, 2 weeks ago, we've done with the discussing of two-qubit gates, right? So another gate we discussed was the swap gate, and the important case of the measurement gate, which measures a particular qubit and returns the result to the classical register. All right. So then we consider this example of GHZ states, which is a generalization of a Bell state to a multiple qubit systems. Okay, so Bell state is a entangled state for two-qubit system. GHZ state is a fully entangled state of a circuit with 3 and more qubits in it. So this is the representation of this GHZ state in the case of 3 qubits, right? And then we've run several simulations using Qiskit quantum simulator. We learned how to launch the simulations, and we didn't get the result of the quantum simulator because there was a long line to the quantum machine. But today I checked that our project was executed, and here is the result. So I remind you that it was the Bell state test. Okay, so first we simulated the circuit consisting of the Hadamard gate and CX or CNOT gate, which creates the Bell state. First, we simulated this state using the classical simulator, which mimics the operation of a quantum computer. And we've got two possibilities, right? Either 0-0 state or 1-1 state. So our Bell state, which we generate with this circuit, collapses either to 0-0 or 1-1, and nothing in between. So just two state in the classical perfect case. In contrast to this classical simulation, the quantum machine gives us not only, so this is the result of the executing of this circuit, and the result consists of 0-0 and 1-1 states as we expected to get, but also it gets states 0-1 and 1-0, which we didn't observe in the classical simulation case. Okay, so these extra states, they come because, I mean, due to the imperfectness of, or because of the real parameters of the real quantum computer. Nothing is perfect, and of course quantum computer is far from being perfect. And after how many 4,000 shots, the most of them still collapse to either 0-0 and 1, but it also provides some contribution from the 0-1-1-0. And of course, if you run, like if you give it more shots, more runs, this contribution from this extra states, it will be suppressed, or we can for a large number of shots we can get rid of their contribution to the result. Of course, this result, this Bell state test, depends on the type of the machine, and I find another result from some time ago. I ran the same test on another machine, also for the 4,000 shots. And there was the result here. So this is the result for another machine. This one was for which machine? Yeah, so IBM Qito, and the previous one was IBM Lagos. Okay, so it's another quantum machine. And here I would say that the result even like worse. So we still get 0011. They are measured, but we still have this contribution from the state 0110, which are this contribution is larger than in this previous case. So this machine gets it worse. Okay, so it works with larger amount of inaccuracy. Right. So this is the result of the last lecture simulations, and now let us proceed with another chapter. Okay, so the chapter number 4. Let's call this one quantum algorithms. Quantum algorithms. So we're gonna dedicate several lectures to quantum algorithms, and today we're gonna start with two simple topics. The first one, 4.1, let's call this one golden signal qubit circuit. And the concept of interferometer. Okay. Interferometer. So let us consider quickly this single qubit gate, Hadamard gate. And I remind you that its action is in the creation of the perfect quantum superposition. For example, from the 0 state, it creates the state 0 plus state 1, and from state 1, it creates state 0 minus state 1. Okay, so it flips the basically the phase of the second term of the state 1. And yeah, so and for example, if I consider 2-qubit circuit with two Hadamard gates, and give 0 0 in the input, what would be the output? So in the input, using the tensor product operation, right? We can write this like 0 0, which is 0 0, but I remember the order, right? So the rightmost is the first one, and then second, third, etc. Okay, so after the application of two Hadamard gates to each one, we get this new state 0 plus 1, then again tensor 1 over square root of 2, 0 1 for the second qubit. And if I expand the parentheses, I would get 1 1/2, and then state 0 0 plus state 0, 1 plus state 1, 0 plus state 1, 1. State 1, 1. All right, so so for 2 qubits, I've got 4 states. So in the first case, we've got the number of states or number of amplitudes to the power of 1. In the second case, to the power of 2. And in general case, if I consider n qubits, I would get 2 to the power of n quantum amplitudes. In general, 2 to the power of n amplitudes. 2 to the power of n amplitudes. And if n number of qubits is large enough, 30, 100, then this number is colossal. It's a huge number. So why it's so important? Let's consider a simple circuit, and we will call this golden single qubit circuit. So I have 1 qubit, okay? Then I put Hadamard gate, and I say that using this Hadamard gate, I create the quantum interference or open up quantum interference. Okay, then I put another qubit. Let's put phase qubit p phi, and then I put another output Hadamard gate, which closes up quantum interference. Okay, it's opens interference. This one closes interference. And this qubit in the middle does something to the phase. Namely, this phase qubit is given by its matrix 1, 0, 0, e to the power of I phi, as we discussed some time ago. Right, and now if I go layer by layer for the input 0, right, I will get 0 in the first layer, then I apply Hadamard, which creates state 1 over square root of 2 0 plus state 1, right? Or the same can be rewritten in the matrix form as 1 over square root of 2, 1, 1, right? So then I apply this phase gate, which consists in the application of this matrix to this vector, 1 over square root of 2, 1, 1. And this operation gives me the result 1 over square root of 2, 1, e to the power of I phi. Or it can be written as 1 over square root of 2, 0 state plus e to the power of I phi, state 1. Okay. All right, and then I apply another closing Hadamard gate to this state. And when I get, I've got 1 over square root of 2, then 1 over square root of 2 state 0 plus state 1. Okay, then plus e to the power of I phi 1 over square root of 2, 0 state minus state 1. Okay. And now I take 1 over square root of 2 out from the parentheses. We got 1 over square root of 1 over 2. And then I've got 0 state plus state 1 plus state e to the power of I phi state 0 minus e to the power of phi state 1. Okay, and now I group the state 0 and state 1 in here, so I get 1 over square root of 1 over 2, then 1 plus e to the power of I phi state 0 plus 1 minus e to the power of I phi state 1. Okay, so what are these coefficients, these terms? So let's consider 1 plus e to the power of I phi. Okay, now I use this Euler's formula to represent the exponential function. It gives me 1 plus cosine phi plus I sine phi. Okay, now I use the cosine and sine of double angle. Okay, so there is a formula, for example, for cosine alpha. Cosine alpha can be represented as cosine square alpha over 2 minus sine square alpha over 2. All right, in our case alpha is phi, and sine alpha is given by 2 sine alpha over 2 cosine alpha over 2. Okay, so I use these two form, and I also represent one as cosine phi over 2 square plus sine square phi over 2. All right, so what I've got, cosine square phi over 2 plus sine square phi over 2 for the unit, then plus cosine square phi over 2 minus sine square phi over 2, then plus 2i sine phi over 2 cosine phi over 2. Right, so here I can cancel down this sine. Cosine plus cosine gives me 2 cosine. So it's gonna be 2 cosine square phi over 2 plus 2i sine phi over 2 cosine phi over 2. Okay, so now I factorize this 1 cosine phi over 2. So you get 2 cosine phi over 2, and in parentheses cosine phi over 2 plus I sine phi over 2, which is nothing but e to the power of I phi over 2. Okay, so I got 2 cosine phi over 2 e to the power of I phi over 2. So this is for this is for the first term, for this 1 plus e to the power of I phi. All right, this is the result. For the second term with minus, I would get minus here, right? And then I would have minus here. And then when I represent, and I will also have minus here, of course. So then when I represent using these formulas, I've got minus here plus here minus here, right? And then instead of canceling sine, I would get canceling cosines. So I would get 2 sine square phi over 2 here with plus, and then minus here, and then I would take the sine phi over 2 out from the parentheses, and in the parentheses I would get minus, so I took also minus I out, and then I get 2 sine phi over 2 e to the power of I phi over 2. Pretty good, looks good. All right, so combining both results, I can write the the final psi vector out from this from this single qubit golden circuit in the following form. So it's going to be cosine up to this factor 2, which is just normalization factor, or can be normalized to acquire the actual value of the normalization factor. E to the power of I phi over 2 state 0, then minus I sine phi over 2 e to the power of I phi over 2 state 1. Okay, so this is, as we once discussed, this is the global phase factor, which doesn't affect the inner products or outer products of the vectors, because e to the power of I phi over 2 and minus I phi over 2 gives me 1. So we can omit this global phase factor and write the psi state and the output of the circuit as cosine phi over 2 state 0, then minus I sine phi over 2 state 1. Okay. So on the other hand, in the most general case, the state of any qubit can be written as C0 state 0 plus C1 state 1. And if we compare the both expressions, we conclude that C0 gives us cosine phi over 2, and the state coefficient C1 is minus I sine phi over 2. So the probability of finding 0 in the output, which is given by the absolute value squared of the coefficient C0, is equal to cosine squared phi over 2. On the other hand, the probability of finding the state 1 after the measurement of the circuit in the output is given by absolute value C1 squared, which is exactly sine squared phi over 2. Okay. On the other hand, this cosine squared can be rewritten as 1/2 1 plus cosine phi, and this one is equal to 1/2 1 minus cosine phi. All right, so we can represent these states. So these states or probabilities of finding 0 or 1 depend on the value of the phase gate. All right, and if I plot these probabilities as a function of the phase phi, they would look like this. So it would go down, then up, then down, then up, etc. So this is the probability of finding state 0. 1, 0, and this is gonna be pi, 2 pi, etc. So for the phase 0, cosine is 1, 1 plus 1 is 2, 1 over 2 over 2 is 1, so probability is 1. And if we measure the circuit in this state, for this phase, we can find only the state 0 in the output, and the state 1 wouldn't be measured for the perfect quantum for the perfect quantum system. On the other hand, the probability of finding state 1 goes like this. Okay, so for example, when the phase is pi, it's not possible to find the state 0 in the output, but the probability of finding state 1 is 100%. So for the perfect quantum system, we wouldn't be able to find 0 state, and we find state 1. And in any case, in general, the result of this circuit, or result of the measurement of the circuit, depends on the phase of the phase gate between the Hadamard gates, between the input Hadamard gate and output, or opening and closing Hadamard gates. So this is the way how we can control the probability of finding the states. So overall, this circuit, this system, is known as Ramsey interferometer. Ramsey interferometer. Ramsey interferometer. And we can realize this quantum interferometer using the IBM quantum composer, for example. Right, for example, so we need just one qubit, and just one qubit. And then I open up the interference. Then I put the phase gate. And then I close up the interference. Okay, so we see that for this phase pi over 2, as we expected, the probabilities of finding the either state is 50%. It's perfect, 50%. So now I can change this phase of the phase gates. For example, I don't know. Let's put for pi, right? And for pi, we've got just state 1 in perfect agreement with our findings. For the phase 0, we would get just state 1 and never state 0 and never state 1. And in general, for any other phase, we will get something in between, like some contribution from the state 0, some contribution from the state 1. Yeah, so this is how we, and of course, without this second Hadamard gate, the result does not depend on the phase. So we need to close this circuit, this quantum interference by the second Hadamard gate to enable to create this in order to be able to see this effect of quantum interference. All right, I stop the share. Show my screen here. All right, so why it's so important? It's important because in the general case of quantum computing, in general, we quite often, if not always, have something like this. So for a system with a number of qubits, we create the quantum interference, like open up the quantum interference by applying the Hadamard gates to every qubit. Hadamard, qubit 1, qubit 2, qubit 3, all the way down to qubit n. Okay, and then we do some computation and we close the quantum interference by applying the second set of Hadamards like this. Okay, we create interference, close interference, and we can do something in between. Like here, we can apply some another quantum circuit, which operates with the quantum amplitudes. Let's call this like some function, and this function can be controlled somehow. This is pretty much how like almost any quantum algorithm operates. We have computer, we create quantum interference, we operate with the amplitudes, and then we close quantum interference and measure the result. So schematically, it can look like we have something in the input, some probability amplitudes in input. Okay, and then we do the computation, quantum computation, and the result of the quantum computation is some particular amplitude which is amplified on the over the level of other amplitudes. Okay, so for the real system, these quantum amplitudes always non-zero, right? They're always there, but we can design the algorithm in a way that we amplify the state that corresponds to the answer to a particular problem. Okay, like for example, if you're talking about this Grover algorithm, we have some array of amplitudes in the input. We design this function f for searching the particular element there, and then, for example, in just single shot or a number of shots, we have got the probability or state distribution with the amplified state of the answer of the element that we are looking for. Okay, and this Grover's theorem states that this algorithm of searching such an element is much faster than the classical search over all the elements. We will discuss this probably next week, but today if it's all clear, we go to the second part, to the second section of this chapter, and it's called quantum teleportation. Quantum teleportation. Teleportation algorithm. Quantum teleportation algorithm. So what is quantum teleportation? So before we're talking about quantum teleportation, we need to discuss this no cloning theorem. So no cloning theorem, which is quite easy to grasp. So in classical physics, when we have some kind of state and we can, or we want to copy this state or transfer this state, we can easily measure it, right? Like, for example, if I have some field distribution in a resonator or in a circuit, like a potential or current in a circuit, I can easily measure this potential and then write it down to a memory, for example, or I can record it and create another state like this in the similar circuit. So we can measure the state and recreate the state somehow, or in other words, we can clone the state. In quantum, we cannot clone the state because due to the measurement of a quantum state, the state collapses to another allowed eigenstate of the system. Okay, so in quantum, we can't measure, or we can't clone a quantum state because, or due to the measurement. In the result of the measurement, the state collapses unavoidably collapses, so we can't prevent it. It collapses to one of allowed eigenstates. Okay, like take a hydrogen atom, create a quantum state of superposition between different energy levels. Okay, in any case, after the measurement, this atom, it will collapse to either state, and this is of course not the initial state, not the state you want to clone, you want to copy. So no cloning theorem. No cloning theorem states that we can't clone a quantum state, except maybe for some trivial quantum states like ground state, right? So if you know that the system is in the ground state, then it's trivial. We can, of course, prepare a system in a ground state. So here we are talking rather about a general state of a qubit. So if I have a state like C0, eigenstate 0 plus C1 eigenstate 1, then I can't clone this state. But what we can do with such a state, we can destroy the state in one place and teleport it to another place or teleport it to another qubit. We can teleport the quantum state or in other words transfer it to another qubit without measurement without measurements. Okay, so this without statement without measurements is important. So we actually don't even, or we couldn't even know what state we teleport. So without knowing the state, we still be able to teleport the quantum state. And at this point, usually people introduce these two guys, Alice and Bob. Alice, we denote her by A, and Bob, hence B. All right, so Alice and Bob, two persons, and so let's suppose Alice and Bob create the entangled state. For example, using the controlled X two-qubit gate. So let's suppose we have Alice, we have Bob, they have qubits, and at some point they create a shared state or entangled state, like this. And we suppose that Bob has, his qubit initially in the state 0, and the Alice's qubit is in the state that she wants to transfer or teleport to Bob. It's a C0 state 0 plus C1 state 1. Okay, so she wants to teleport this this state to Bob. So after before that, before the CX gate, in the first layer of the circuit, the actual state is the tensor product of the two, right? So it's a C0 0 plus C1 1 of Alice's qubit, and then tensor. Should we actually write a secondary? So I write Bob's qubit first, 0, and then tensor Alice. Okay. So the result is C0 state 0 0 plus C1 state 0 1. Okay. So then after the CX gate, we get what? So the control is Alice's qubit and target is the Bob's qubit. So the control here is C, target is T, C, T. So the result of application of the CX gate will be C0 state 0 0 plus C1 state 1 1. So we flip the target qubit because control is 1. All right, so this is indeed entangled state. If C0, C1 equal to 1 over 2, 1 over square root of 2, then it would be Bell state. Otherwise, this is just entangled state. Okay, so now what Alice can do with this state? So first, she can, I mean, of course, she can measure her qubit and try to transfer any information about her initial state to Bob. And the first try or first thing she can do is to measure this qubit or her qubit in the same basis 0, 1. So if Alice measures her qubit in basis 0, 1, so what would she get? This after the measurement of or measuring this state in the basis 0, 1 collapses the state either to state 0, 0 or state 1, 1, right? So it collapses the state to either 0 or 1 on the Bob's side with probabilities is modulo C0 squared, modulo C1 squared. Right. And she has no control over the exact result of the measurement, right? After each measurement, the result will be random, but after the measurement at the Alice's side, she will know the state of the Bob's qubit because it will be exactly the same state, either 0 or 1, because we have here only two possibilities, 0, 0, 1, 1. Right? So for example, if she measures something like 0, 1, 1, 0, 1, 1, 0, etc. at Alice's state side, then Bob gets exactly the same string 0, 1, 1, 0, 1, 1, 0, etc. And this is something called shared randomness. Shared randomness. Shared randomness. They get exactly the same strings of binaries 0, 1. I mean, of course, for the perfectly entangled qubits, of course, systems are not perfect, as we discussed in the beginning of today's lecture. And in reality, of course, there will be some discrepancy, but in general, overall, or in the perfect case, they will get exactly the same binaries, sets of the zeros and ones. But this is not what our initial purpose, right, or our initial goal, to send or teleport the state from Alice to Bob. And in order to do so, Alice can measure the state in other bases. For example, in the basis plus minus. So if Alice measure the state in plus minus basis, What if? In order to check this, we need to convert first the state 0 plus Alice of the Alice's qubit into the plus minus. So we know that plus state is 1 over square root of 2, state 0 plus state 1, minus is 1 over square root of 2, state 0 minus state 1. And from these two equations, we've got the formulas for the state 0 and for the state 1 in terms of plus minus. 1 over square root of 2 plus state minus. And this one is 1 over square root of 2 plus state plus minus state minus. Okay. So now for this state after the application of CX gate, what we've got? We've got C0 state 0 0 plus C1 state 1 1 entangled state. And I remind you that the first one is Alice, second is Bob. Alice, Bob. Okay, so now Alice converts her measurements or her equipment from measuring the states in the 0 1 basis to the basis plus minus. And so let's write this up to these coefficients here, they're constants, and let's omit them for simplicity, for make all this more manageable. So this one is C0, state 0 at the Bob's side, and then we have the 0, which is plus minus in the plus minus basis. And for the second one is C1, state 1, state plus minus state minus. Okay. Expand the parentheses, gives us C0, 0 plus C0, 0 minus plus C1, 1 plus minus C1, 1 minus. Okay. Now I combine the terms with state plus and state minus. And what I will get C0 state 0 plus C1 state 1 times state plus C0 state 0 minus C1 state 1 state minus. All right. So again, measuring her qubit in the basis plus minus again gives us two possibilities. Either the first one or the second one with the corresponding probability in there in the parentheses. So and what is more important is that if she finds her qubit in the state plus, then she immediately knows or concludes that the Bob's qubit is in this state in the parentheses. This one or this one, depending on her result. Right. So after the measurement in basis plus minus, it collapses to either plus, which gives the state at the both sides C0, 0 plus C1, 1. And this is exactly the initial state that Alice wants to send to Bob. Sends to Bob or teleports to Bob. So if she detects her qubit in the state plus, then she immediately knows that her qubit state teleportation is successful. Bob gets the correct state at his end. However, if she finds her qubit in the state minus, then the Bob's qubit is in the state C0, 0 minus C1, 1. So the phase is flipped, right? So then Bob needs to do something to correct the state to get the actual initial state. What he can or should do is to applying the z gate, right? That converts the flips the phase. Then Bob has to place bit flip operation Z. So, but of course, Bob doesn't know which operation, either leave the qubit state unchanged or applying this Z control gate. So Alice has to send the information to Bob through the classical channel. Then Alice has to send either 0 or 1 to Bob using the classic channel. And then Bob applies this Z operation to the power of I. Let's say where I is either 0 or 1. So if it's 0, then no need in Z correction. If it's I, Bob needs to correct the phase to the at his end. All right. So how how is it implemented in the in terms of circuits? So in order to implement this one in terms of circuits, I suggest that we consider another program, another useful simulator called Quirk. So this is quantum simulator, and one Quirk instead of IBM Quantum. It's nice and like well representative, and also allows us to show the time evaluation, like the dynamic or operation of the circuit in dynamic. All right, so in order to create the circuit that implements this quantum teleportation, I first I need to create another like third qubit here. How I do so? I can do it, for example, by creating the entanglement between the second and third. Then I need to entangle the first and the second. Okay. Then I need to put the Hadamard on the second one. So the first and the second qubits are the Alice's qubits. Okay, so this circuit will be a 3-qubit circuit, which is like more advanced, but it implements the same operation. So the first two is the Alice's qubits, and the third one is Bob's qubit. All right, so the state of the qubit that we need to teleport is the first one. Second one is auxiliary qubit, and at the Alice's side. And the third one is the Bob's qubit, as already said. All right, so then I need to put the Hadamard here and measure the first one and the second one. Then depending on, so after the measurement, you see this line, it was second line, right? After the measurement, it became double line. Here, double line means the classical register. And so now after the measurement, depending on the result of the measurement, I need to apply the X control, but classically controlled gate to the third qubit. Okay, I do this way. So if the result is 0, then this X qubit doesn't work. If the result is 1, then it applies the action of this X qubit. Okay, so it works only if the input is, or control is 1. And then the second Z qubit, depending on the state of the first one. All right, and and I also put the block sphere to represent the state of the input. Okay, of the initial state of this first qubit, and this is my output in the circuit qubit. Okay, so now I compare the state of the first and the third one, Alice's qubit and the Bob's qubit. All right, so as I can see, they both are in the same state, and of course, if I change the state from 0 to 1, I observe that they still point in the same direction. For the plus state, still in the same direction, minus the same, I the same. So these two states are completely, perfectly the same. But what if I need to check this function depending on different dynamics? Okay, so if I apply this X rotation, so rotation of the qubit in the around the X direction, I see that the output, this output qubit, this third qubit, gets exactly the same quantum state as the state of the first one. I can also add the rotation around the Y axis, and it still completely copy the state of the third qubit, copies the state of the first one. And if I add, for example, Z direction, it still works perfect. So using this circuit, we teleported the state of the first qubit to the state of the third qubit. All right. So this circuit is a little bit more difficult to or different to the circuit that we discussed in the lecture. And how it works, you can, for example, write down the states in each layer, or using this block sphere approach, you can see the quantum states in every layer, in every qubit of this circuit. Like this. Right, and basically see the dynamics of the circuit in every qubit and on each layer. All right, so yeah, Quirk is a very nice platform for simulations. One can find a nice tutorial on YouTube of using this platform. So this is basically it for today. Let me stop the recording. And thank you very much.